We will introduce our featured speaker. I'm very excited to introduce Dr. Jason Kalirai. He's going to kick off our first featured talk of this event. Dr. Jason Kalirai is the Mission Area Executive for Civil Space in the Space Exploration Sector. He joined APL in November 2018 and is leading the implementation of innovative and cost-effective solutions to critical civil space challenges by developing space science missions, instruments, and research programs. Prior to joining APL, Dr. Kalirai served as the multi-mission project scientist in NASA's Telescope Science Institute. He has published over 100 research papers on topics related to stellar and galactic evolution and has won numerous awards for his achievements. Dr. Kalirai earned his Bachelor's of Science in Physics and Astronomy, his Master's of Science in Astrophysics, and his PhD in Astrophysics from the University of British Columbia. He completed his postdoctoral fellowship as a Hubble Fellow at the University of California at Santa Cruz. Jason's talk is entitled Space Exploration at Johns Hopkins APL. Jason?
Hey, Chris, thank you so much for that introduction. Can I get a quick sound check as well as a slide check? Are you able to see my slides?
We can hear you and we can see your slides.
Okay, great. Well, thank you so much, Chris, for that introduction, and thank you to the organizing committee for putting on this very important workshop. We wish we could welcome all of you in person here at the Johns Hopkins University Applied Physics Lab. I know many of you have visited our beautiful campus before, but we also have some new members who have not, and we look forward to that opportunity in the near future. But we have several hundred people on here, which is really great to see. This is a very important topic, and we want to thank you for bringing your expertise on future opportunities in flight software. So Chris asked me to share a little bit of background about the lab and highlight some of the work that we're doing right now. So this will be a very general 20-minute overview presentation, and then I'll turn it over to Steve Thibault, our chief engineer in the sector. So I want to start today with this beautiful picture of our campus here in Laurel, Maryland. So as background, the Johns Hopkins University Applied Physics Lab is one of 14 university-affiliated research centers in the USA. These are strategic organizations that are partnered with the university and that maintain critical capabilities that the government can leverage to address critical challenges. We are the largest UARC, largest university-affiliated research center. We have many sponsors across the work that we do at APL, including Department of Defense agencies, NASA, as well as other government agencies. We've gone through a lot of growth over the last several years. We're about 7,000 staff members right now at APL. Almost all of them are in our Laurel campus. We do have a couple of other satellite campuses across the country as well. And our vision is to create defining innovations that ensure our nation's preeminence in the 21st century. Very important vision statement. As the lead of the civil space mission area, as well as my colleagues that lead the other 11 mission areas at the lab, we try and matrix all of our new opportunities, all of the work that we're doing on behalf of the nation, against this vision statement and be fairly selective in the kinds of projects that we're taking on. Just as background, APL was established in the early 1940s, and so this was a tumultuous time. This was during the midst of World War II. One of the major developments in World War II was the V2 rocket. The Germans built over 3,000 of these V2 rockets. You can see a picture here of one of them launching. And so APL was just getting established during this time, and after the war, the United States was able to get their hands on some of these V2 rockets, many dozens of them, and they began experimenting with them and seeing how we can turn these instruments, which were weapons of destruction, into scientific exploration vehicles. And so some of our first engineers and scientists at the lab were dreaming of the space age in relation to these kinds of capabilities. And so one of them was Dr. James Van Allen, who was one of the founding members of the lab. And Dr. Van Allen and his team. He was serving on an advisory committee at White Sands, where some of these rockets were being launched from in the US. And the engineering teams there on one of the first launches decided to put a camera as a hosted payload on one of these rockets, and they launched the rocket into space. And this is the actual video from 1946 of one of these V2 rockets. It exceeded the von Karman line, and you can see this beautiful panorama that's being captured by that small camera that was pointed out of one of the windows, and then they ejected it and retrieved it on the ground. But this is the first image of a planet taken from space, and that was taken by the Johns Hopkins University Applied Physics Lab. And so, the lab, wasn't set up for, space exploration as its primary endeavors initially, but space exploration has been a part of the DNA of the lab since its founding days. So a little bit about the sector. So in the space exploration sector, we have two what we call mission areas. So I head up civil space. We also have the national security space mission area, which is headed up by Patrick Binning. Right now, about 75% of the work that we do in the sector is in civil space. 25% is in national security space. If you look at our history from those founding days, we've launched 70 missions. A lot of these are, custom solutions to specific science problems. We have over 300 instruments and sensors and payloads. In the space exploration sector for the civil space work that we do, our primary sponsor is NASA's Science Mission Directorate. We're also involved in some work with the Space Technology Mission Directorate. We also do a little bit of work with NOAA and the National Science Foundation. And you can see a list of selected first there. I won't go through the whole list here, but starting with that first picture from Earth, and then just a decade after that, after the Russians launched Sputnik, APL was very proactive, very curiosity driven to not only determine what the Russians were doing with Sputnik, but also turn that problem around, right? So if you can measure where Sputnik is at any given time, you know what its orbit is, you can flip that problem around and use a spacecraft to identify where you are on planet Earth. And so that was how we developed the first satellite navigation system, which was called Transit, which ended up being the precursor of modern day GPS. And then you see lots of firsts there with respect to some of our first national security space programs and some of our more recent civil space programs. The framework that we have at the lab here is really to look at the full end-to-end development of space missions. This starts with scientific research. We have a large team of scientists that are actively pursuing questions in planetary science and heliophysics and astrophysics and earth science and other areas. But then we have the full capabilities at the lab to conceive, design, build, test, and operate spacecraft and instruments that are going to address those science questions. And so there's lots of layers of engineering that is wired into this flow. And of course, smart partnerships. We're always looking for smart partnerships to help partner with us on these developments. In the sector, we really leverage cross-APL capabilities for achieving the goals of our space mission development. And so you can see some of those capabilities here. Not all of these capabilities enter into every mission that we put together, but certainly flight and ground software does. And so you can see that called out there. And in fact, it's an area where one of the big strengths of APL is experimenting in artificial intelligence and machine learning. It's a big focus, and we try and leverage that in the sector, and we develop algorithms and then implement those algorithms on both software as well as FPGAs, and then fly those on our missions. And I'll give you a couple of examples today, and then you're going to have many experts speaking on that very topic later today as well. You also see at the bottom there a capability that we have at the lab called RED. That's the Research and Exploratory Development Department. This is a state-of-the-art facility for electrical design, electrical fabrication, mechanical design, mechanical fabrication, additive manufacturing, and it's another example of a capability that really flows into almost all of our work that we do in the sector when it comes to developing hardware. And here's a snapshot, a fleet chart of all of the major missions that APL has developed in the last 25 years or so. And it's a kind of an unprecedented view of everywhere that we've developed a piece of hardware that has explored the solar system. And our primary focus is in planetary science and heliophysics, the study of the sun and how the sun influences our solar system. And so you can see, on the right there, you can see a mission called NEAR. That was the first planetary science discovery mission, the first mission ever to visit an asteroid and orbit around that asteroid. New Horizons, I'm sure many of you have heard about. That was our mission that we launched in 2006 that visited Pluto. And then after Pluto, a Kuiper Belt object, a fossil of the early solar system called Arakoth. You see that wing that's going up towards the sun. Those are some of our major heliophysics missions that are studying space weather, as well as the sun and how the sun influences bodies, including the Earth, in our solar system. And on the left-hand side, you see several examples of just bold, one-of-a-kind planetary science missions that we're working and developing at APL. Europa Clipper is an example of the biggest mission that we have right now at APL, where we're in a strategic partnership with JPL and mutually developing this flagship mission. And I'll say a couple more words about some of the specific programs on here, but you can see that these are really one-of-a-kind concepts to address specific science challenges outlined by NASA and even by the National Academy of Sciences through the decadal survey process. So let me start with Parker Solar Probe. This is our most recent launch from APL. We launched Parker Solar Probe in 2018 after roughly a 10-year development process. But the mission actually has its roots back into the 1950s. It was identified as one of the top priorities for heliophysics. And essentially the goal is to build a spacecraft that could fly right next to the sun and could orbit around the sun and do in situ measurements and capture the source of the energy that we measure from the sun and study that. And the problem here, of course, is technology. And so there were a number of innovations that APL led the development of to enable such a mission. First and foremost, the thermal protection system. You see a nice picture of it here. This is a 8-foot wide, 4.5-inch thick carbon composite shield that can reach temperatures of 2,500 degrees Fahrenheit, right? The surface of the sun is about 5,800 degrees. This shield can reach 2,500 degrees Fahrenheit, and all of the science instruments and the electronics that you see in the spacecraft are in the shadow of that thermal shield. So that thermal shield will always be pointed directly towards the sun, and it protects the spacecraft from heating up as a result. We have some new technology in our solar panels as well, where we use a water-cooled thermal management system, essentially pumping water through the solar cells to cool them and then radiate that stored heat back into space. First time that we've used that technology on a space mission. Some state-of-the-art instrumentation, including an exposed solar cup that you can see kind of hanging off the side of the thermal shield there, that's made of specialized materials that allows it to withstand thousands of degrees. And then what was really mission enabling for Parker was an innovative mission design that leveraged multiple flybys of the inner planet Venus to successively drop the orbit of Parker Solar Probe closer and closer to the sun. So let me give you an example of that. This is a bird's eye view of our solar system. I'm going to run this movie here in a second. You're going to see the planets orbiting around the solar system, and Parker is going to drop off from Earth as soon as I start the video. There it goes. Hopefully there isn't a large lag. And so when we came in on our first perihelion pass in 2018, Parker was 15 million miles from the sun. But what happens here is if you look at this next orbit, as Parker comes out here, you're going to see it's going to fly right past Venus right there. And we take advantage of these repeated flybys by Venus to give a little bit of energy from the spacecraft to Venus and then subsequently drop the orbit of Parker closer and closer to the sun. This is what allows us to do the science that we're shooting for with Parker Solar Probe. So we started 15 million miles from the sun. In a little more than 2 years, we're now about half that distance. We're about half that distance, and we're still going to cut that distance significantly. So eventually, Parker is going to orbit the sun at a distance of just 3.8 million miles. Keep in mind the sun's 500,000 miles across, so you're traveling through the corona of the sun, scratching the surface of the sun, and you're able to do science and take measurements that you just can't do when you're sitting at Earth 100 million miles away from the sun. But flight software is essential to the success of this mission. In fact, all of us, our hearts kind of stop for a couple of days every time we enter one of these perihelion passes, because we can no longer communicate with the spacecraft when it's in one of those phases. And so for a couple of days there, we're typically waiting on edge for the beacon tone. And so it's a wonderful automated system that's been performing flawlessly well. Over 150 science papers have already emerged from Parker, and it's really redefined our understanding of the sun and the detailed workings of the sun. So very successful mission that we just launched from APL that flight software is a very important part of the success of the mission. Parker was a mission that we just launched. We're also about to launch a mission in which flight software is the critical ingredient to seeing the success of the mission. And that's a mission called DART. It's the Double Asteroid Redirection Test. This is a unique mission where we're essentially investing $300 million to build a spacecraft and then take that spacecraft and collide it into a body and destroy it. That's the goal of the mission. And so what DART is intended to do is demonstrate a technique that we can use to potentially mitigate an asteroid impact on Earth by slowing down that asteroid using a kinetic impactor technique. So to show you this, I wanted to highlight a video that was captured. And so this is from about 7 years ago. And there you see an asteroid headed towards a city in Russia called Chelyabinsk. And this asteroid exploded right on top of the city. This is a very populated city, more than 1 million people. And you can see some cell phone footage here of what that looked like when this asteroid exploded. There was about 20 times as much energy released in this explosion than in the atomic bomb. And you can see some very scary footage here of people that just survived. So there's the glass ceiling breaking right in front of somebody who was almost right underneath it. You can see an office setting here where a gentleman is hurled through a window as that explosion occurred. And then the last one is very scary. You can see school children here. And if you watch the window, you'll see the shock wave of that explosion. And the kids are terrified. The teacher is terrified. There were a lot of injuries in this event. And so the Earth, our planet, is being peppered by these asteroids all the time. Every couple of weeks, we've got something coming in that's a meter-sized asteroid hitting us. Once a year, we get something that's much bigger, the size of a table. And then once a decade or a couple decades, we get something much larger that can cause a kind of catastrophic impact on our society and our infrastructure and our health. And so NASA stood up an office called Planetary Defense to deal with this. And that office aims to do three things. That is, identify all near-Earth objects, characterize them so we can understand more about their properties, their orbits, their sizes, their compositions. So if they were to hit Earth, we could assess in advance what the impact would be. And then the third one that you see on the bottom left there is mitigate. Develop the technologies that are required to mitigate a potential asteroid impact on Earth. And then DART is the first mission in the Planetary Defense Program that is aimed at that third goal of mitigation. So what we're doing with DART is we're targeting a binary asteroid system. And so this is a beautiful example of doing this in a very safe way and a way in which you can really measure the impact of the experiment. So this binary asteroid has a primary system that you see off to the right in this picture that's called Didymos. So that primary asteroid is about 1 kilometer across, a little bit less than 1 kilometer across. And then the small asteroid that you see orbiting the primary is called Dimorphos. And that's an asteroid that's about 150 meters across. And the small one takes about 12 hours to go around the large one. And so the goal with DART is to come in, hit the small one head on, right in the middle, and slow down its orbit around the primary. And we're predicting that we can slow down its orbit by about 10 minutes. Flight software is critical to this. The problem that we have here is that we know very little about the object that we're going to hit. So you can see a picture of the Didymos asteroid system, the binary system. You can't resolve it, right? You see the single picture of it in the left there. That's taken through a very large telescope, an 8-meter ground-based telescope in Chile. And then this is what we think in the middle picture, what the shape model of the primary asteroid looks like. Of course, we're not hitting the primary, we're hitting the secondary. We can't even see the secondary in these images. So what does Dimorphos look like? We don't know, right? We see lots of different types of asteroids out there in the solar system, but we don't actually know what this object looks like. And for us to achieve the maximum impact of deflecting its orbit, we really want to hit it right in the center. And so this is where flight software comes in. It's going to be a couple of hours before impact that we actually resolve the system using the Draco telescope that's on DART. And then we have this, we're going to have autonomous navigation where flight software called smart navigation algorithms that were developed at APL for other purposes are being refactored and applied to the DART mission to centroid on the smaller object and provide the autonomous course corrections to the spacecraft such that we not only zero in on the smaller body, but then given the shape and the orientation of the smaller body, we locate the center of that smaller body and we hit the center of that smaller body. So a great example of a really exciting NASA mission that's going to put planetary defense on the map. But the success of the mission ultimately is dependent on the incredible flight software that's being developed to zero in and hit this asteroid. So very exciting mission. This is DART is going to launch later this year. It's been very challenging in the COVID environment to integrate the spacecraft, but the teams have just done a heroic job here. You see these are very recent pictures of some of the critical pieces of technology, including the NEXI ion propulsion engine there that you see in the middle panel being installed on DART. And so we're in our INT phase right now, and we're putting this mission together, and we're looking forward to launching it later this year. And then finally, I wanted to highlight, one of the most exciting areas in all of, space exploration right now, and that's the study of our solar system's ocean worlds. And the Earth is one of those ocean worlds. And for a long time, we thought that the Earth was the only ocean world. It was the only world in which we see an ocean. But it turns out that the Earth may be unique in that it has a surface ocean, but not in that it has an ocean. There are many moons in the outer solar system, large moons of Saturn and Uranus and Neptune, that we now know contain subsurface oceans. So Europa is a great example. That's why we're building a Europa Clipper, which is a flagship mission that's going to do repeated flybys of Europa to assess the habitability of that moon. One of the most exciting moons on here is Saturn's moon, Titan, which is also an ocean world. And we proposed at APL a couple years ago to build a mission called Dragonfly, which is a nuclear-powered octocopter. It's a dual quadcopter that will study Titan using a method that we've never done before in the solar system, and that's to essentially fly on the world. It'll conduct experiments both on the surface, but then it can also pick up and fly on Titan to traverse to its next destination. The reason that this is possible is because of the characteristics of Titan itself. Titan is an ocean world. It's Saturn's largest moon, but it has a combination of factors that really make it amenable to flight. One is a low surface gravity that's only 1/7 of Earth's gravity, and then the second one is a much denser atmosphere than Earth. So imagine a lot of air and very little gravity, perfect place to fly. It has an Earth-like geology. That picture that you see there, those are clouds. Titan has rain on its surface. It has surface lakes and of methane that we've seen. It has a very stable temperature. It's a water ice composition. So Titan has all of the ingredients for life, and really represents a view of what the prebiotic chemistry on a world looked like, and gives us hints into what the past conditions on Earth might have been. It has complex organics on its surface, has 2 different types of solvents with its methane, as well as its subsurface water ocean, has all energy from sunlight, photochemistry. So it's a very, very exciting destination to explore. And so Dragonfly will come into Titan. Titan's atmosphere is so thick that it just acts as a cushion. It'll slow down the descent vehicle, and Dragonfly will transition to autonomous flight. And this is where flight software comes in again. And so Dragonfly will itself, it'll come in, it'll fly, it'll find a safe place to land on the surface of the moon. After it lands, we have a packed set of science instruments, including seismometers and drills. We have mass spectrometers. We have a gamma ray neutron spectrometer to measure composition. We have cameras. We have a lot of science instruments, and we'll use those to study Titan. And then Dragonfly will pick up, it'll fly, and it'll use terrain relative navigation algorithms to identify its next place to land, and then autonomously safely land and carry out another phase of its scientific exploration. So very exciting mission that we're going to be launching later this decade in 2027. And we're just beginning the development of here at APL with a lot of very, very strong partners. Many of you come from organizations that are partnered up on the Dragonfly mission. So we're really excited about that. And then finally, kind of looking forward, one of our goals at APL is to enable the next level of exploration for humanity, right? It's in our DNA as human beings to want to explore, to want to push further than what we can see or what we can dream of going to. And we're developing a mission concept called Interstellar Probe, which does exactly that. Interstellar Probe it would be a large heliophysics mission where we would build a spacecraft and shoot it out of our solar system at very high velocity and travel beyond the edge of our solar system. So this is a spacecraft that would travel into interstellar space. It would not only do very exciting science on the way to interstellar space by doing, for example, planetary flybys and passing through the heliosphere of our sun and measuring the composition and the shape of that heliosphere, which is a long-standing problem in heliophysics. But it would also have a modern set of science instruments that could do exciting astrophysics science and planetary science from its eventual vantage point, which could be somewhere between 500 and 1,000 astronomical units from the sun. So this would be humanity's first intentional steps beyond our solar system. And it's a mission unlike any other. It's a mission that would have to be designed to last for 50 plus years. It's a mission that would have enormous communication challenges, challenges in repairing itself, really very autonomous systems in deciding which of the many types of scientific data that it collects are going to be the most exciting, the most important for space exploration, and then sending those data back to Earth. So that's a quick snapshot of some of the missions that we're developing at APL right now and that we've recently launched. And there's many different engineering practices that need to come together to enable these kinds of systems. But flight software is one that cuts through all of them and is just the critical ingredient to seeing the success of many of these programs. I want to close by showing you a snapshot of a new website that we just developed for APL Civil Space Program. I was only able to talk about a couple of our programs here today, but we have a lot of great information on this new website. The link is at the bottom there. You can also just Google APL Civil Space, and so please explore this website and learn more about the work that we're doing for our sponsor, NASA. So with that, I will stop and I will turn it back over to Chris.
All right, thank you so much, Jason. That was a very interesting talk. So we have a couple of questions in the Q&A, and I had one myself, which maybe I'll start off with that one. What are your thoughts on, so my experience from mission to mission, there's a lot of siloed technology in terms of, in teams that you would stand up teams for specific missions. And it seems like a challenge going forward as systems get so much more complex and our software gets so much more complex, that trying to, make sure that we have the right organization and framework around sharing these technologies from mission to mission, especially when there's an organization that's doing multiple missions. And just wondering if you had any thoughts on organizational challenges with respect to how we can share and collaborate across missions.
Yeah, so Chris, I think that's a great question, and a big piece of it is communications, right? And our, one of the things that we're very fortunate at APL is to have, investments from the lab in developing some of those technologies that might be in an early, immature state initially, but can benefit these kinds of missions going forward and enable, new exploration. And so, one of the things that I feel like we really need to do better is have, better forums for discussing those technologies. And so, for example, we invest at the lab, we invest a lot of money into new IRAD technologies that can enable not only civil space programs, but a lot of the programs across the lab. And I really think we can share those technologies better as well. And that's one of the goals, in fact, on that website. It also is, if you go to that website right now, you won't see, kind of technology development that's happening in civil space right now. It's on the to-do list to kind of get that there. And then also put together, not only workshops for, NASA-based technologies, but also reports and annual reports and, brochures and documents and things like that. But overall, and that's just the kind of the seed funding that you have for developing those technologies. But also when you build a mission like Parker Solar Probe, there are these state-of-the-art technologies that were created to enable the success of that mission. I think it's a good question on how do we, even if we're not doing that science experiment, how do those same technologies flow into other opportunities? And in some cases, these technologies are so amazing that it can change the whole perspective of what kind of science questions you're even asking that you might be able to address because of those technologies. And then, the place where I really enjoy learning about that are big aerospace, conventions, space industry conventions and conferences like Space Symposium, and, really talking to our peers and, getting these ideas. And, it's a great time to be involved in this and to be asking that question because of, the rapid growth in the space industry for all things related to, space flight development.
Absolutely. Thank you so much. And looking at that repertoire, there was a lot of challenging missions and some very significant challenges on the horizon. All right, let's see. There's one other question that just came in. All right. How do you plan to power and thrust the interstellar medium? What are the main lessons from the Voyager missions?
Yes, that's a great question. So how do we plan to thrust the interstellar probe mission? There's a couple different options there. One option would be to drop the similar to Parker Solar Probe. Imagine dropping the spacecraft down in towards the sun and then doing an Oberth maneuver, so doing a slingshot around the sun and shooting the spacecraft out. Even with that approach, you would have to get to reach the kinds of speeds that we need and to get to 1,000 astronomical units in a reasonable amount of time. You would have to come in much closer to the sun than Parker Solar Probe has, and possibly carry an upper stage with you and then ignite that upper stage as you're doing that closest maneuver. So that's challenging, but there are people working on that. In fact, we have an internal investment program at the lab right now looking at a solar powered rocket. There's also what we're planning to do for our baseline approach for interstellar probe is really to leverage the advances being made in developing very powerful rockets, right? So with modern technology, with for example, an SLS type framework, we think we can build a spacecraft, with adding an upper stage with a giant, very powerful rocket. And achieving those velocities, that would still require, for example, at Jupiter flyby, where you're able to get a little bit of an extra kick. And so with that, kind of the lessons learned from Voyager. Voyager was a mission that had a design for planetary science measurements. Voyager did this grand tour with flybys of all of the outer planets. It did not, it wasn't, built with the set of instruments that would be optimized for the kinds of heliophysics research we want to do in the heliosphere. And so for interstellar probe, it would be optimized for that science, but we would take advantage of some of the same kicks that we can get from outer bodies to get further out into the solar system faster.
Excellent. And then one last question before we go over to Steve Thibault. How does Parker avoid asteroids in space?
Okay. Very little you can do there. You're not gonna maneuver the spacecraft along a specific trajectory to avoid an asteroid, but the probability of that is very, very small, right? So Parker is it's a small mission, and that space is huge, right? So you've got this orbit that's going 100 million miles out to the sun, back into the out to near the Earth, Earth and Venus, and then back into the sun, and so just the random chance of colliding into an asteroid is insignificantly small, so it's not a worry.
Right. Okay. Thank you very much, Jason. It was a very interesting talk.